All right. So, hello everyone, and welcome to Make Learn 360. So, sorry for the delay. Um, so we can now start. Kindly share the link to your friends so that they can also join. Thank you. Please kindly share the link to your friends so that they can also join. So, in about 5 minutes' time, I will start. Thank you. All right. So, please share the link, and I'm going to start in 5 minutes. All right. So, all right. Okay. So, I think we can start now. Okay. So, today I want us to first of all look at the bending moment and then the shear force diagram. And then after that, we will come back and look at torsion. Um, and then we will look at the principal stresses or more circle. Okay. All right. So please kindly share the link to your friends so that they can also join. Okay. Okay. So let's start. Um, so we have a beam here, and then we want to look at the shear force and then the bending moment diagram. So first of all, you have to look at the um so let's look at the reactions at the support. So one, find all the reaction forces. Find all the reaction forces. So let's try and find the reaction forces. Okay, so you are going to use equilibrium of a rigid body. You are going to assume that the whole of this body is actually in equilibrium. Okay, and when a rigid body is in equilibrium, what are the conditions that apply? So for a rigid body to be in equilibrium, summation of forces positive in the x direction will be 0. Again, summation of forces positive in the y direction will also be 0. And then finally, summation of moment about any point in the plane, let's say point B, so will be 0. Okay. Now these three equations are necessary and then sufficient for the body to cause it to be in equilibrium. All right. Okay. Then you go back to the diagram and then you ask yourself, so at this joint B here, um sorry, because this joint B here is a hinge, we will expect something like so only one reaction force. Let me use another color so that you can get it well. So there is a hinge here, okay, which is having only one two reactions because it's actually a hinge. So there is another reaction here. Let's call it BX. But when you look at the joint D, you are going to see that we have some sort of a roller support. Okay, you can see some small um balls, so it's like a ruler. Okay, so D is a ruler and then B is a hinge support or a pin support. So for a ruler, there is only one reaction. For a ruler, there is only one reaction. So dy. Okay, now this is what we call the free body diagram. Okay, when you have the forces and then the direction of the forces and where they are going, you get what we call the free body diagram. All right, so now this is what you are going to do. You are going to start off by saying that we will sum forces along x, along y, and then we'll look at the moment. So first of all, let's look at the summation of forces. Okay, first of all, let's look at summation of forces. So if you are looking at the summation of forces, then we have along the x direction, we can say that we have bx. Okay, we have bx, and then we also have what? So apart from bx, there is no force in the x direction. Okay, so there is no force, so then we can say that bx is equal to 0. In other words, there is no force in the um, horizontal direction. Okay, now let's come to summation of forces in the y direction. Okay, so if you take summation of forces in the y direction to be 0, then you do the same thing. Okay, so if you look at that one too, it's going to be So 20 kilonewton here is coming down, so it will be minus. So minus 20, and then by here is going up, so plus by. Then we have 40 kilonewtons, which is coming down, so minus 40. So minus 40, and then we have point D here, so that one will go up, so plus dy, and that gives us 0. Now basically it's going to be by plus, so by plus dy should be equal to 20 plus 40, which gives us 60. So basically we can say that by plus dy is 60. Let's call this equation 2. As a matter of fact, the first one was equation 1. Okay. Now, okay. So now, with what you have right now, what do you see? So by plus dy is 60, but in one equation we have two variables. Okay. So in one equation you have two variables. It means that we need another variable, isn't it? All right. So now what do? We have to take moment. Okay. So now let's take moment. Let's take the moment. If you take the moment, you can choose a point where you take the moment. So we are going to assume that we will take the moment about, let's say, point B. Okay. So if I take moment about point B, so counterclockwise is positive, and then should be equal to 0. And then I'm going to take moment of all the forces from B. So essentially, this 20 kilonewton here will have a moment, and the sense of the moment is going to go in this direction about point B. So that one is going to be like counterclockwise. So 20 multiplied by 2.5. So 20 multiplied by 2.5. Then we have the 40 kilonewtons, which is having a moment in this direction. That's sort of clockwise. And then so 40 multiplied by 3, right? But then it's clockwise, so minus 40 multiplied by 3. So we are assuming that clockwise is positive and counterclockwise is counterclockwise is positive. No, let me look at it again. So clockwise is rather positive. So if that is the case, then the first one was 20 kilonewtons, which was counterclockwise. So it's going to be negated. The first one will be negated, but the second one, because clockwise is positive, it's going to also be positive. Okay. So sorry, 40 multiplied by 3. All right. And then let's look at another moment here from D. That's basically in the direction here, which is anti-clockwise. But then the moment arm is what? 3 plus 2 is 5. So 5 dy. Okay, so plus 5 dy. Okay. I think it's actually counterclockwise about point B. So that is it. So this should be equal to 0. And then if you solve for this one, what are you going to get? So basically f dy is equal to everything which is here, and just negate it, right? So I'm going to get minus 20 multiply by 2.5, and then plus 40. So plus 40 divided by 3. Now after doing this, so that's 70, and then you divide by 5. So basically you get 70 here, then you divide by 5. um so essentially what you have done here is that you have actually solved for the reaction forces, the reaction force at point D. But then I think it has to be negated, because if you look at it, minus 20 multiplied by 2.5 plus 40, um um, yeah, so it's supposed to be negative, because it will come here as 5 dy, um should be equal to minus 70. So dy is actually minus 14. So dy is 14 kilonewton. Now the minus sign here is basically telling us that um we have to just look at the direction. Okay, all right, and then um let's solve for the okay, so let's send it back. Send dy equals minus 14 here. So by plus dy is what? 60. But what do you know? You know that dy is minus 14. So by is going to be 60 minus dy. So now this is how it's going to be. By here is going to be 60 minus 14. So by is going to be 60 plus 14, and that's going to give us you know so essentially that gives us 78. Sorry, 74. All right, so now we have dy and we have by. Basically what are we going to do? All you have to do is to now draw the free body diagram again and show where the forces are acting. But then I don't want to redraw it again. I will just look at it and then assign the forces. So for instance, let me give you an example. So at by here, we had by to be 74 kilonewtons. So 74. So 74 kilonewtons. And then there is a point here at dy, and dy was what? Minus 14. Okay, so if we have minus 14 and then the direction is going up, it's the same as saying that the direction will come down, so that here becomes 14. So essentially that is it. Now we have dy as 14 kilonewtons. So now that we have the forces and then everything, this is the best time to draw the shear force and then the bending moment diagram. So shear force and bending moment. Shear force and then what? Bending moment. Okay. So, okay. So then let's start from the free body diagram. Um, so let me try and see if I can sketch it. So I have okay. So I have, let's say this is the beam here. And then at A there is a load of 20 kilonewtons. So this is A. There is a force at A which is 20 kilonewton. And then there's a force at B. B is what? 2.5. And then the force there is going up, which is 74 kilonewtons. So essentially the force there is going up. And then the load there was what? So 74 kilonewtons. And then C was what? So C was basically 40 kilonewton. But the difference between A and B was 2.5. All right, so we have 2.5 meters here. Okay. All right. So now, okay, so that is it for, yeah, 74. And the distance is 3. So basically, there is C here, and then I'm sorry, and then between B and C is 3 meters. And then at joint C, the force is coming down 40 kilonewton. Okay. And then I think finally at D there's a force which is okay, at D that is the 14 kilonewton. Okay. All right. So now the distance here to here, and then um let's say that here is also 2.5 meters. Oh, sorry, it was 2. So essentially, this side is going to be 2 meters. All right. So that is it. Now, this is what we are going to do. We are going to draw the shear force and the bending moment using this question. So this is what I normally do. Okay. Um. Okay. So now, any questions, please? Up to this point, do you have any question? Any question, please? Okay.